So thanks for introduction, and my name is Hao Pan, and today I will introduce the work of our group, mQRCode. Secure QR code uses nonlinearity of spatial frequency in light. So QR code is a near-field communication method with rapid readability for many mobile devices with camera, and it has many applications such as social, e-card, mobile payment, electronic tickets, access control, and so on. QR code is popular in countries. More than 45% of population use mobile payments in China, and the amount of transactions through WeChat and Alipay is over $3,100 billion in 2016, which are both based on QR code communication. However, QR code is not secure. QR code attack is revealed in recent researches, and crimes related to QR code payment is also reported in recent news. So let's envision a mobile payment scenario. A customer shows a payment QR code on his phone screen, and the cashier scans it to complete the transaction. And as customers in line for payment, and they may prepare the payment code in advance. So the attacker can take a picture by his mobile phone to the customer's payment QR code in advance. And it can also use a ported camera to take a picture of the payment QR code. So once the attacker obtains a picture of the victim's QR code, there is no need for him to decode it. The attacker can simply submit the captured QR code to other cashiers or use customized software that simulates the checkout code to make payment. So in this way, the cashiers will deduct money from the victim's account, and the attacker can successfully finish one illegal transaction. And these are real-world cases that happen in Shanghai. The attacker used someone else's payment code to deduct multiple illegal transactions, and it is difficult for the victim to find the attacker because the victim is hard to detect where the payment code was taken. And the primary cause of this attack is due to the nature of light communication, where the communication range is very wide. Therefore, when a customer shows a QR code on his screen of his mobile phone, and the cashiers can easily scan it. And however, at the same time, other cameras around the customers can also capture an image of the QR code, and then they can perform an attack. So that is to say, the range of the communication becomes the range for the attack. So how to solve this problem? And our basic idea and solution is to reduce the attacking range from the entire non-line of sight area to a small area in the space. So in this way, only the legal cameras, like the cashier, can obtain the QR code information. And attackers that are out of the attacking range cannot obtain the information of the QR code. So therefore, the target of our work is to reduce the attacking range of the QR code to improve the security. Meanwhile, our solution should not impose additional costs to users, like adding new hardware or communication channels, so user can use QR codes as usual and do not need to change their user behavior. So to do that, we propose to utilize the nonlinearity of spatial frequency. So what is spatial frequency? Spatial frequency is a characteristic of any structure that periodically occurs from position in space. So let's use a 2D spatial frequency as an example. The left pattern has F1 frequency, and while the right pattern has F2 frequency. And when these two spatial patterns meet, the resulting pattern, there will appear another spatial frequency, that is F1 minus F2. And this is the nonlinearity of the spatial frequency in light. And specifically, we can express this phenomenon by formulas. The periodical spatial patterns can be expressed as cosine functions, and when these two cosine functions are multiplied, the result of them has two nonlinear parts, F1 plus F2 and F1 minus F2. Because our human eyes are more sensitive to low frequencies, so we can see F1 minus F2. And the spatial frequency is everywhere, and it also exists between the camera and the display. So the camera has a color filter area, and which is used to obtain the color information. And this color filter area has a specific spatial frequency. And the display is composed of a number of pixel points. the pattern displayed by the pixels can constitute a specific spatial frequency. So therefore, when we use a camera to take a picture of the display, it is common that a low frequency, colorful noise pattern appears. So this is the nonlinear interaction between the camera and the display. So the filming can be used to design a secure light communication technology. Specifically, our target is to design a specific pattern on the display, which seems be random to human eyes and illegal cameras. So when a legal camera captures a pattern at the correct position, the nonlinear interaction between camera and display reveals the original QR code. So how to achieve this? From the theory of the spatial frequency, we learn that when two spatial patterns are superimposed, the resulting pattern can be calculated in the form of multiplication, since the camera and the display are also the spatial frequencies. So we have the same theory to model their behaviors. The CFA pattern of the camera is known, and the QR code is also known. So we can compute the pixel pattern of the display, which is our encrypted QR code. And in our paper, we use the imposed schemes to make the black and white box in the encrypted QR code less distinguished by designing different phase functions and add noise patterns. So we leave these details to the reader because of the limited time. So why we choose nonlinearity in spatial frequency to design the secure QR code? It is because the spatial frequency of the display projected on the camera changes across the distance and the angles. So when a camera captures a picture of the display at correct distance and angle, the magnitude of two frequencies are similar. So in this case, F1 minus F2 is evident, so the original QR code can be recovered. And on the other hand, when the camera and the display are not located at correct distance and angle, the spatial frequency projected on the camera changes, so which causes the F1 becomes greater or smaller than F2. As a result, F1 minus F2 becomes not evident, and the camera cannot recover the original QR code. So summarized above, only the camera located at the correct position can capture the original QR code, where the camera at other positions cannot recover the QR code. So therefore, the taking range is reduced. So here we give an example of the mQR code, and the first figure shows the original QR code, and where the second is the encrypted QR code. And when we capture the correct distance and angles, the original QR code is revealed as shown in this one. And when the camera is in other positions and the original QR code is not revealed. And this is a demo video of our mQR code. And we change the distance between the camera and the display. So when the camera is in the correct position, and the original QR code can be recovered. Yeah. So we test our system with 10 cameras and 10 displays. And when the camera and display are located at the correct position, the accuracy of decryption rate is high. And moreover, when the distance is 10 larger or smaller than the correct distance, the decryption rate drops from 100% to 0. And similarly, when the angle is 10 degrees offset from the correct one, the decryption rate drops from 100 to 10%. So, in conclusion, mQR code enables secure QR code applications, and we present a novel visual encryption method using nonlinear interaction between camera and display to improve the security of QR code communication. And our method doesn't need to add any other hardware or communication channels. So users can use it for mobile payment as original QR code and don't need to change their user habit. So this is my talk. Thank you for listening.